For the Introduction to Epidemiology course, in the module Measures of Association, this is the third lecture segment, Odds Ratios. So odds ratios are the measure of association for a case control study. So when we think about a case control study and we look at the same 2x2 table that we've thought about for cohort studies and randomized controlled trials, you can set up the four basic conditions for your study subjects in the same way. You can have the rows exposure or treatment, yes or no, and the columns disease or outcome, case or control. But if what we've done is a case control study, and we've selected cases based on the outcome, and then we've selected some random sample of the theoretical cohort as our controls, can we then calculate incidence in the exposed and incidence in the unexposed in order to determine the risk ratio? That's what we would have done for a cohort study, but we cannot do that because the ratio of cases to controls was determined by the study sampling plan and does not reflect incidence. So what we can calculate is within each of those groups that we've sampled, the cases and the controls, we can calculate the odds of exposure among the cases and the odds of exposure among the controls. So we could do that by looking at the column for cases. A is exposure yes, C is exposure no. So odds of exposure in the cases is A over C. And then odds of the exposure in the controls is B over D. And that's often rearranged if you ask someone how do you calculate an odds ratio, they'll go A over B divided by C over D. But that's actually just a little junior high school math type thing, and they've rearranged it. I like to do the one on the left because it actually shows you the odds of exposure and the odds of exposure, which is the true basis of the case control study. But this other one, A over B divided by C over D, is going to come in handy a little bit later. So how do you present an odds ratio, or for that matter a risk ratio, when you're setting up your table? I don't think I talked about this in the last segment. I showed you some examples of some decently set up results tables. So this example that I'm showing you is actually, gee, that's my name at the bottom. It's one that I set up. So this is the way we epidemiologists like to set up our tables. And I thought I would point out a couple things. These are odds ratios, and it's important to set up a table in a way that there's no ambiguity to your reader of what is being compared to what. So in this table, the first line is no use of oral contraceptives, and we show you how many breast cancer cases and how many controls reported no use of oral contraceptives. And they become what's called the referent category or the reference category ending with a CE. I'm not sure why some people use one and some people use the other. I've used both. But that is the unexposed category, because I've called it reference, that all the exposed categories are going to be compared to. Because in reality, we could do a 2x2 table just as I've shown you in those simplified diagrams. And in that case, the exposed condition would be any use of oral contraceptives. And then I'm showing the number of cases and the number of controls that reported that. And then I've calculated an odds ratio for being a case and any use of oral contraceptives compared to controls. And of course, that odds ratio indicates a very small difference and wide confidence intervals, not indicating any statistical significance for that comparison. But frankly, based on prior literature and some prior hypotheses, I further broke down the exposed category into 4 different subgroups according to when they reported their most recent use or their last use of oral contraceptives. So within 5 years, 5 to 9, 10 to 19, and so on. And so then I've calculated an odds ratios for each of those subcategories, and those are still being compared to the no use as the referent category. And hopefully once you get used to it, that's clear. I'm not calculating an odds ratio for more than 20 years ago compared to 5 to 9 years ago. I'm calculating odds ratio for more than 20 years ago compared to no use, because no use is in the same table and it still has one referent category. So anyway, this can apply to risk ratios as well, but I just put this slide in here to remind myself to talk about when you're setting up a table, be sure that it's clear what is the comparison category and what's the unexposed category. And also that in epidemiology, we actually like to put the numbers, the columns with the count of the case and control in the same table with the odds ratio. Your statistical software will spit those out in different places in your output. You just have to find them and put them together. Okay, and here's another example of a table presenting odds ratios. And this is one that I'm going to use as my, I'm sure this is a perfectly good paper with perfectly good data, but the way they've structured their table and the way they've presented it, I'm not a fan of, I'll put it that way. So if we look over at the right, they have the full model, the odds ratio, 95% confidence intervals, and P. So the first row of the table says EGFR less than 60 mils per minute per whatever that means. The EGFR less than 60. Odds ratio of 2.74. Well, compared to what? And maybe if you're a nephrologist, you're used to this and you know that EGFR less than 60 is compared to EGFR more than 60, but I don't know, maybe they're comparing it to EGFR more than 90, or maybe I don't know what they're comparing it to, and they're not saying in the table is my point. And then age parentheses year, odds ratio 1.09. What on earth would that mean? Do they have 1-year-olds and 0-year-olds in their data set? Of course they don't. That's actually the odds ratio for each year of age. So the person who is 67 has an odds ratio of 1.09 compared to the person who is 66. And the person who is 66 has an odds ratio of 1.09 compared to the person who is 65. That is what the software will do. If you put in your age variable as the age in years of each of your person and you put it into multivariable model, it will spit out an odds ratio, and the odds ratio will mean the odds ratio for each single year of age in that variable, which is not the easiest thing to interpret until you're used to it. So very often people prefer to put categories of age and actually say, so our reference category of age is 50 to 54, and then here's the odds ratio for the people who were 55 to 59, and here's the odds ratio for the people who are 60 to 64 compared to the 50 to 54. And then, odds ratio for male gender, you have to stop and think, well, the comparison group is probably female, but they could have shown it, so on and so on. So they've tried to cram in a lot of information into this table, but I'm kind of an advocate of making it straightforward for the people that are trying to read your paper and look at your tables and show the reference categories. Okay, so going back to the odds ratio as a calculation and the risk ratio. So we are usually using the odds ratio as a stand-in or as a way to represent the risk ratio. The real cause and effect relationship that we're interested in is the risk ratio, is the risk of incident disease or the risk of whatever outcome we're studying. How does that compare in our exposed to our unexposed or our treated to our untreated group? And the true expression of that comparison is the risk ratio, because we're interested in comparing those risks. The odds ratio, we're comparing the exposures. So why is it that the odds ratio is used all the time to represent the risk ratio? And the answer is just a little bit of the way these tables work and the numbers work. So if you look at our 2x2 table again, if the disease is rare, that means that A, in a cohort study, A is a very small quantity compared to B. If the outcome is rare in the overall population, then A is a very small quantity compared to B, and also C is a very small quantity compared to D. So when we do the calculation for a risk ratio on the left, the risk A over A plus B is the risk in the exposed. C over C plus D is the risk in the unexposed. Now, if A is very small compared to B and C is very small compared to D, then A over B divided by C over D is really the same thing as the risk ratio. And A over B divided by C over D is the rearrangement of the odds ratio calculation that we saw a couple of slides back. So for those of you who like to think of these things a little bit in this kind of notation, that may be helpful. For the rest of us, most days we just remember that the odds ratio is a way of is a calculation, and the result of it is interpreted as a risk ratio, and the condition of the outcome being fairly rare is necessary for it to be interpreted as a risk ratio. And so this is a little graphic that is showing on the horizontal scale the disease incidence in the unexposed in a theoretical study population, and on the vertical scale what odds ratio we would calculate at different levels of the risk ratio. So if you look on the far left where the disease incidence is 5% or 10%, those odds ratio dots are pretty close to the specified risk ratio for each group of dots. So the risk ratio of 1.5 are the round dots, and over by values of 0.5 and 1, they sure are falling very close to 1.5. Where we start to deviate is when the either the risk ratio gets higher. So if you look at the risk ratio of 3, which is the triangles, as the disease incidence gets higher, even as high as 0.15 and 0.2, the odds ratio starts to deviate a fair amount from the risk ratio. So there's no, there's no final cutoff for, what is a rare disease to meet this assumption, but certainly, less than 5%, you're doing great, and less than 10%, the odds ratio is used all the time to represent the risk ratio. So just some of those things we were looking at in numbers. Two other things about whether the odds ratio can be used to represent the risk ratio. The first bullet is that the exposure prevalence among cases in the study is generally equivalent to the exposure prevalence among all such cases theoretically eligible for the study, or all cases in your theoretical cohort. So what we're saying there is, have you done a correct job of ascertaining your incident cases, and the cases that you have studied truly represent the cases from the underlying population. The second bullet is that the exposure prevalence among controls is generally equivalent to the exposure prevalence among all persons in the population from which the cases arose. So again, did you truly randomly sample your controls from the theoretical cohort? So simpler ways of saying those two things is that your cases are representative and your controls are representative. And those are actually, sampling your cases to be representative and sampling your controls to be representative are not the easiest things to do. And so we worry a lot about bias in case control studies, because if we are off, if our cases do not correctly represent the exposure prevalence among the true group of cases, or if our controls don't correctly represent it, then our odds ratio is going to be biased. And then the third assumption, where the odds ratio represents the risk ratio, is when the outcome is relatively uncommon in the population. And that corresponds to the previous slides where we talked about the disease should be rare. So thinking about all the different measures that we've addressed in these segments so far in this measures of association module, a good way to summarize is to look at all the different measures and think about what are the units, what are their possible ranges, and what are their null values. So hopefully to help you interpret when you see data in a paper. If they're talking about a risk difference, which is, if you recall, it's done by subtracting the risk in the two exposed and unexposed groups, the units are going to be the units of risk. When you subtract two things with the same units, your answer has those units. And then the range can be -1 to +1, assuming that you've divided out and represented your risk as 0.1, 0.01, however you've represented it. You subtract those two numbers, and they can't exceed +1 or be less than -1. The null value for a difference is going to be 0. When you're subtracting things, if they're exactly the same, there's no difference in risk, then the null value will be 0. The risk ratio is unit list. In fact, if we go down the column, all the things that are called ratios all are unitless, because you have your numerator that has certain units of risk or a rate, and you have your denominator that has the same units of a risk or a rate, and those cancel and you have a unitless quantity. The range for a risk ratio or an odds ratio is from 0 to infinity. So with 1 being the null value, if the risk in the exposed group is less than the unexposed group, the risk ratio will start to be below 1 by being 0.9, 0.8, 0.5, 0.2, 0.1, 0.01, and so on, with 0 being the lower limit. An incident rate difference. So recalling from the module on measuring disease frequency, a rate has time in the denominator, or reciprocal time, as I like to say, or some kind of numerator per unit time. And so the range of differences when you subtract those two things can be anything really, negative infinity to positive infinity. And the null value, because the difference is subtraction, the null value is 0. And then incident rate ratio and hazard rate ratio, similar to the risk ratio, we're dividing things so they're unitless, and the range is going to be 0. So if the risk is lower in the numerator, if the risk in the exposed is lower, you're going to be getting 0.9, 0.8, 0.7, and so on. And if it's higher, you're going to be getting 2, 4, 6, 8, up to whatever. One more thing I'd like to mention is that all the situations we've talked about so far in this module have been applying measures of association to situations where we're looking at some kind of incident outcome. The risk ratio, risk difference, rate ratio, odds ratio are usually used to compare occurrence of incident events. However, the odds ratio or risk ratio can be applied to prevalent disease when reporting cross-sectional data, or other prevalent conditions. The prevalence of hepatitis C virus was one example that we had talked about. So if you have two different groups and you want to compare their cross-sectional prevalence of hepatitis C virus, you can calculate an odds ratio or a risk ratio. So if you're going to use these measures in that way, for clarity, I would suggest that you term it, we calculated the prevalence odds ratio, or we calculated the prevalence risk ratio.